We'll go ahead and get started. We're happy that Joe is here today. And Joe has some questions that I think, what did you say, you and Scott had been working on or something like that?
Me, Scott, and Aaron.
You, Scott, and Aaron. We'll do that. Let me get through the material first, let people get started on the homework and so on, and then I'll stop the camera and all that kind of stuff, and then we'll talk about your problems.
Scott needs it too, so you should.
Oh yeah, okay, Scott needs it too. Maybe what we'll do is we'll cover this part first, and then we'll keep the camera running while we talk about it. That sound good? All right.
Talk about problems.
What? I'm not ready for, I'm not really all that prepared. I meant to get prepared and answer, if I had the answer handy for his questions by the time the class started, and then Trig ran forever. So, that's okay. We'll discover the answer together. That's fun. All right. This is one long chapter in this book, and we are up to, I don't know, what are we at, 4.9 or something like that now? I don't even remember. It's getting to be long. I think there's only one more, 4.8. 4.8, L'Hôpital's rule. I love that name, L'Hôpital. There. L'Hôpital's rule, I believe. L'Hôpital's rule. L'Hôpital's rule is kind of a neat little trick. It throws us back, though, to limits. And I just keep not liking the whole limits thing. Not that I know it's important, but I mean like as in we do more fun things in this class than limit stuff. But that's okay. L'Hôpital's rule is important. It has lots of applications and so on. We need to talk about L'Hôpital's rule. And L'Hôpital's rule is a nifty little rule that comes into play whenever we're talking about something that is a ratio. Did I just get rid of my nice pen? Which one did I steal? If you've got some kind of ratio, like you could write the numerator as some kind of f of x, and the denominator as some kind of g of x. You know, as one does. Like, for example, maybe the numerator is something like x squared minus 9, and the denominator is something like, I want to make something that's going to break.
0.
No. All right, let's just do this. This is not the world's greatest example ever. We actually already had some problems kind of like this earlier in the course. I mean, f of x could be this x squared minus 9, and g of x could be x minus 3, and it's a thing. And you could make graphs of this. Heavens, you could even find like the derivative of this thing using your quotient rule. It's all neat and powerful, except at one place. Notice that this goes to hell at one place. What's that one place?
3.
3. Right? At x equals 3, all hell breaks loose.
Wait, if it's 0 divided by 0, that wouldn't...
Aha! You have, yeah, what do you want to do with it? At x equals 3, here, I'll just write it this way. At x equals 3, I don't even know what to do with this. Because what happens? The numerator becomes 0 and the denominator becomes 0.
But if the numerator and denominator are the same, then it's 1.
Oh, it sounds like it should be maybe 1?
But they're both 0.
But it's dividing by 0, which means it's infinite. But another way to write this would be 0 times 1 over 0. 0 times anything is 0. I don't know how to determine the answer here, right? Things go wildly wrong at x equals 3 when it's not at all a bad thing. I deliberately chose my use of words there. I said it's hard to determine what the answer is because this is an indeterminate form. There is an, if you get it to this point, the answer, this is an indeterminate, I don't know if I'm spelling it right, indeterminate form.
I know what you're about to say.
You do? What am I about to say?
No, I can't say it.
What?
Because I don't know the whole part. I just
Okay. So,
I know the summary.
so here's the deal. I mean, this is a perfectly happy equation. I can put any old number except the 3 in there. It's going to work, including things really, really, really close to 3. In fact, we're not going to even go just too bad if it was like 3.00001. It would still work. But at 3, things go wrong. Now, your book then says, hey, what we really mean here then is what we really want to say is we're looking for the limit as x approaches 3 of this thing. So as x gets closer and closer and closer to 3, where are we getting? Okay? I'm happy with that. You can teach about L'Hopital's rule without making it about limits, but since your book is making this about limits, let's do that. And the reason why I think they're making it about limits and they're phrasing it this way about, like, think about it as you're getting as close as you can to before you hit that place where things go wrong, is because earlier we've had a few limit problems that were like this, where you might remember, I don't know, section 2, chapter 2 or something like that, you did some factoring. I mean, this particular one, we could factor to be x plus 3 times x minus 3, then we could cancel the x plus 3 and the x minus 3 and we'd be okay. Here, let's go do that over here. We could have changed this to x plus 3 times x minus 3 over x minus 3. We could have canceled this out and we get the value is x plus 3. So our limit, this should be 6. Okay? Using the school skills we did in like section 2.4 or something like that. But plenty of the ones that we're going to be seeing today, you could not have done that way. Okay, this particular one that I'm just pulling off my frontal lobe here was not the greatest example. You've done something like that before, but I get it. That's why they're doing this. But it turns out, if you are talking about some kind of problem that is a ratio, but you care about it, where it's a ratio between two different expressions, two different functions, and at the place you want to know the answer, it's this indeterminate form, 0 over 0, we have the magic of L'Hopital's rule. L'Hopital's rule tells us that if you want f of x over g of x, and f of x equals 0, and g of x equals 0, so you're getting yourself into the form where you've got a 0 over 0, then this limit as the x approached whatever, let's just say a, of this thing, is equal to, shockingly, f prime of it at that value divided by g prime of it at that value. What? What? So if we get to one of these places where it blows up, instead, just take the derivative of the top. Now, at one of these places where it blows up, this falls apart any place else. I don't want you to think, do not think, so f of x over g of x equals f prime of x over g prime of x. No, no, 1,000 times no. But yes, if we're at one of those places where it's an indeterminate form of 0 over 0. Okay? L'Hopital's rule works, but only at those indeterminate places. Any place else, this isn't going to work.
So even if it's 5 over 0?
Yes. This is only working for certain kind of problems. The 0 over 0s. It's also going to work, as we're going to see in just a minute, for the infinity over infinity problems. Okay? But, so like, if it's a 0 over 0 problem, like the numerator evaluates as 0 and the denominator evaluates as 0, you can say, yep, this is going to work. You put this back as an equal sign here, and it is the derivative of the top divided by the derivative of the bottom. Like, for example, over here on this one. In general, it will not work to take the derivative of this divided by the derivative of this. But because at x equals 3, this is a 0 over 0 kind of problem. L'Hopital to the rescue. Take the derivative of the top, which apparently is 2x. Take the derivative of the bottom, which is 1. The answer is 2x, but this is at x equals 3. So it's 2 times 3 equals 6. And son of a gun, it's the same answer as we got over here. It's the weirdest damn thing. But it does Does not work everywhere. It only works where you get that indeterminate form. But if you've got some kind of equation, let's come up with another one here. Let's grab one of the ones from the book. So what's our conditions here? L'Hopital's rule works if you're trying to figure out the value of some kind of ratio where the top and the bottom are functions, but both the top and the bottom, the numerator and the denominator, evaluate to 0 at the value of x that you care about. So, for example, alright, I like this one. Sine of x over x. That's a function. We should be able to make graphs of it. We have probably done things like that. We've probably computed the derivative of this thing. We've probably, that would be a quotient rule problem with a trig rule problem inside of it. We have done these things to death. But if I wanted to know the value of this at x equals 0, things go to heck. Because if x equals 0, the numerator, the sine of 0 is 0, and the denominator is equal to 0. We get a 0 over 0 problem. Everywhere else it's fine. Plug in the value x equals 1, plug in the value x equals 10 million, plug in the value 0.0001, it works. Here it doesn't. L'Hopital to the rescue! Take the derivative of the numerator. What's the derivative of sine? Cosine. What's the derivative of 1? I'm sorry, what is the derivative of x? 1. So this is equal to the cosine of x. So now we just plug our x equals 0 into here, and we get the cosine of 0, which is 1. Cosine of 0. So the limit, as the correct way to write this would be to say that the limit as x approaches 0 of the sine of x over x turns out to be equal to 1.
Wait, what if you didn't find a derivative?
What do you mean?
What if you were just doing, would you have to do the derivative? Because on the last one we did the derivative, didn't we?
Yeah. We had what was it, x squared minus 9 over x plus x minus 3?
Yeah, but
We took the derivative of the numerator and we took the derivative of the denominator?
yeah, but before we did that.
Yeah, before we did that, that particular one, we could fall back on skills from chapter 2, I think it was, where we factored the top into x plus 3, x minus 3, and that canceled. And then we just had x plus 3, that was another way. But that trick isn't going to work over here, right? Where there's no factoring of sine of x and getting rid of things and stuff like that. We didn't have that. This will work at values of x where the original function evaluates to 0 over 0. Your book makes it very clear about some important things about this though. We're not saying 0 divided by 0 equals 1. Although in this case, the limit of this function where the top was approaching 0, the bottom was approaching 0, was equal to 1. But that's kind of more a coincidence here, right? In the other one, it evaluated to 6, right? We don't mean that 0 over 0 equals 6. It's an indeterminate form. It could have been infinity, it could have been negative infinity, it could have been 0, it could have been, it just depends. Okay. L'Hopital's rule, though, comes to your rescue when the function is a 0 over 0 at that location. It also comes to your rescue if the function worked out to infinity divided by infinity. Infinity divided by infinity. For example, what would be, well, let's get one of the ones out of the book so we don't make one up. We do it right. Okay. What would be the limit as x approaches infinity of, let me get that same problem, 3x plus 5 divided by 2x plus 1. Okay. I mean, that thing I have in parentheses there, that's just a function. We could make a graph of it. We could take its derivative and so on. But I mean, if we actually made a graph of this thing, it looks something like this. And going out to infinity on the x-axis, we're approaching some value here. All right. But here's the deal. If I just plugged in, it's hard to plug in infinity. But as x gets bigger and bigger, the numerator just gets bigger and bigger. In fact, as we head out towards infinity, the numerator gets infinitely big. And if we do the same thing with the denominator just gets infinitely big. This is an infinity divided by infinity problem. And as your book walks you through, this could end up being infinity, this could end up being a number, it could end up being 0, it could become a negative infinity. In fact, all the combinations are possible. We need L'Hopital's rule to come to our rescue again, because this is an infinity divided by infinity. It is another indeterminate form. So if we know that this is a L'Hopital's rule problem, and at x equals infinity we can't solve this, all right, take the derivative of it's going to be equal to the derivative of the top divided by the derivative of the bottom. 3/2. This value, as we go out toward x equals infinity, the value is going to be equal to, it's going to be approaching 3/2. So L'Hopital's rule works if it is a infinity over infinity problem, or it is a 0 over 0 problem. I mean, you can see there's other ways you could get infinity over infinity. For example, what if my problem was something like 1 over x minus 4 divided by x squared plus minus 16? Again, we could probably solve this using skills that we learned back in chapter 2, but more importantly, that's actually infinity divided by 0. All right, but you can see how, like, for example, this would be, as you approach 4, this would be 1 over 0, which would be approaching infinity. And you can see how you can get yourself into trouble again. And this side maybe could be, I don't know, whatever. You can see how you can get yourself into trouble, though. And you'll have plenty of examples of those in the problem set. So we got two possibilities here of indeterminate forms. If your fraction evaluates to 0 over 0, use L'Hopital's rule. If your fraction evaluates to being infinity over infinity, you have to use L'Hopital's rule. But here's the deal. There's other situations. Turns out there's a bunch of these other indeterminate forms. Like, what if your function evaluates to being 0 times infinity? That'll blow your mind. What is 0 times infinity? Well, it turns out it can be a positive number, it can be a negative number, it can be a negative number. It can be 0, it can be positive infinity, it can be negative infinity. It's an indeterminate form. So is if your form worked out to infinity minus infinity. If your equation worked out to that it evaluates to an infinitely big number minus an infinitely big number, you've got another problem. Here's another weird one. How about 1 to the infinite power? Ooh, it's a whole weird thing. If your function evaluates to something that works out to 1 over the, here, find the value of x, I don't know. I don't want to make a mistake. You'll see problems on the test. On the problem set. What about infinity raised to the 0th power? What about 0 raised to the 0th power? These are all other weird forms. Here's the deal, though. These kind of problems typically can be solved with L'Hopital's rule, but with modification. We're going to see, not L'Hopital's rule has to be modified. You have to adjust the equation until you can get it into a form you can use L'Hopital's rule. So if you get yourself into one of these weird forms, odds are L'Hopital's rule can save you. We just aren't yet aware how to do that. All right, real quick, let me just look at these pens real quick. Which one's this one? I guess it's this one. take a look, well, when you're ready, in the book. For example, what if you have some equation where you're trying to find, it could be written out as f of x times g of x. But the limit, I mean, like, as you approach some value of x, like this term goes to 0, but this term goes to infinity. Let me give you an example of that, like they have in the book. What if your equation was 1 over, oh shoot, I already lost it. 1 over x cubed plus 1? Is it plus or minus? Yep. And the g over here was 3x squared. As this goes towards infinity, this first term becomes 1 over an infinitely large number. This term goes towards 0, but this term goes towards infinity. This is going to be a 0 times infinity type problem. And what your book tells you to do here is to rewrite the equation in a form that involves a quotient. So instead of it being this weird thing times this weird thing, isn't that the same thing as 3x squared over x cubed plus 1? I mean, that's the same thing. Now it is a quotient, and as x approaches infinity, both the numerator and the denominator are going towards towards infinity. This is now an infinity over infinity problem. Now, L'Hopital's rule will work just fine. Let's actually do it. L'Hopital's rule then says we can take the derivative of the top divided by the derivative of the bottom. Let's see if we can do a little change around here. It's 6 over 3x. As x goes towards infinity, that number, the denominator, is going to get bigger and bigger and bigger. So it's going to be 6 divided by a bigger and bigger number. It's going to be 0. Let's see if that's right. Let me look at that one right here. We had n equal to 3. So, where did I put that? If n equals 2, if n equals 3, it's equal to 0. Yes, okay. So see, the trick was to rearrange the equation until it became a ratio. Now, I don't want to go around reinventing the wheel here. The truth is, this chapter goes through lots of examples, forms where it comes to 0 times infinity, forms where it comes to infinity minus infinity, forms where it's 1 to the infinite power, or it's infinity to the 0th power, all those different things they have up on there. And the truth is, we could spend a lot of time going through all of them. They all have the same basic strategy, though, of rearranging things until you get it in the form of a quotient. Once it's a quotient, then L'Hopital's rule can work for you. Okay? Sometimes you do things like take the log of both sides of the equation. Sometimes you're going to do, but let's just leave it. You'll find that in the book rather than us spending enormous amounts of time on it. Does that make sense? All right, so first things first, let me give you the problem set. And you know what? I'm going to take Miss Sharp her pen back, and I'm going to steal a better pen from her. Okay. So, for today, what did I do with it? All right, L'Hopital's rule, page 470. We are doing problems 357 through 395 on. Okay, sounds good. Now, I am told Joe and Eric and Scott have been hard at work on the problem that involves those linear approximations or whatever. Was that right? That's the problems it is? And got into some problem involving one of the estimates of error or something like that. Is that right? All right, so let's find out what that was. Joe, do you happen to remember which problem that is?
63, I think.
Number 63?
73.
73. All right, hold on. You're right.
63.
63. So this is linear approximations and differentials, and we are on 63? You guys went back and forth a few times, I'm confused. 63?
Yeah, 63.
63. For the following exercises, determine the approximate f of x and a, and evaluate the linear estimate. Calculate the numerical error in the linear approximations that follow. All right, so 63. You're trying to find the cosine of 0.01. All right, and this is that linear approximation stuff. Okay. You're trying to find a linear estimate at 0.01, which is equal to the value f at, okay, so what are we doing here? So f of x is the cosine of x, right? So a is 0, x is 0.01. Are we in agreement on that part so far? Mrs. Sharp, I stole one of your pens. I'll put it back, I promise.
Oh, of course. Yeah, no problem. I didn't want to interrupt you.
And so f of a is 0, okay, plus the derivative f prime of a times the difference between x and a. All right. F of x is cosine of x. Cosine of 0 is 1, right? Plus the derivative of f. Hey, what's the derivative of cosine? Negative the sine? Okay. Hold on, I did this wrong. Let's see here real quick. Okay, so the derivative of this is negative the sine of at a is 0. Sine of 0 is 0 times, I don't really care, it happens to be 0.01. So my estimate is equal to 1. Okay. Let me think about that for a second here. I think I like that answer. Is that what it gives in the back of the book for the estimate? The estimate is 1. Okay. But you guys said that the error on the estimate or whatever was the problem on that one, right? Okay. So we need to know what the actual value here of cosine of 0.01 is. Oh no! After all that. Oh no! Never mind. I thought I was screwing up. Never mind. Okay, so I'm going to get up a calculator. There it is. I'm going to make sure I'm in radians. You guys got a much smaller error, didn't you? I wonder if the answer is you were doing it in degrees.
Actually, it was bigger.
It was bigger. All right, I'm going to switch mine to radians. Let's see what's going on here.
Oh, no, wait, maybe it's not.
Yeah, let's just try the radians thing. Hold on. So what is the cosine of 0.01? Okay, so the right answer of the cosine of 0.01 is 0.99995, and then a ton of zeros before we get to those cents. So 1 minus this number, so clear this out, 1 minus the cosine of 0.01 is equal to 5 times 10 to the negative fifth. Is that what the book gives?
Yeah, we did. I was doing it in degrees.
You're doing it in degrees. Smallest error in the world. Yep. How would you know it's not in degrees? How? Now I mean on your calculator. In this problem. When you looked at problem 63 on this page here, how did you know that that shouldn't be in degrees? There's no degree symbol on what's on the inside. It says cosine is 0.01, not 0.01 degrees. Okay? I don't think that's what you did wrong. I suspect you just didn't notice your calculator was in degrees, right? But, yeah. Okay. Cool! Scott, did you get that? Great. All right. All right, I'm going to go ahead and stop the recorder so I can start uploading this one. And we can keep talking about other problems, or we can work on these limits or whatever. Okay? All right. I also